Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lessons, of course, we did talk about the magnetic force when we have two wires. Today we'll talk about something a little bit different, which is we're going to talk about speakers. You might wonder, what do speakers have to do with magnetic field or force, let's say? And of course, they have a lot to do with magnetic force, you can say, because the base of their work is basically depends on the varying signal, which obviously, or you can say, basically the forces between two magnetic fields. I'll tell you more once we go through this one. But basically, that is the concept for today. So we're going to talk about speakers, and you do know what are speakers, yeah? Basically, in order to have a sound system, or let's say if you have a microphone, let's say, and of course you are talking basically, your talk basically will, you are creating a sound, let's say, and this sound is basically a signal, or you can say it has a wave and frequency. This wave, of course, this compression and rarefaction, of course, will be basically hitting the surface of a microphone, you can say, or you can say there is a small thing called, you can call it something like a diaphragm. This thing, of course, moves back and forth. This back and forth movement, of course, inside, you can say, a magnetic field would cause a varying electrical field, you can say. Or, in a simpler word, we can say this sound signal would be, or you can say this sound will be converted to an electrical signal. And of course, afterward, this electrical signal will pass through the microphone or the wire to the amplifier. There, inside the amplifier, this sound will be amplified by using the means of transistors, which we're going to talk about in later chapters, let's say. And then, of course, after that, this sound or this signal will be sent to this speaker, and then from the speaker, of course, once again, or you can say, will be converted this time from electrical signal into, or varying electrical signal into sound energy again. So, and this is how we can have, or we can hear a louder sound, let's say. All right, for example, when I talk to you, that's a little bit different. When I, for example, or when you hear me through the TV or your laptop, let's say, or whatever the means that you're watching this on, let's say, this, or you can say there's electrical signal that have basically went to the speaker, and then the speaker, of course, will convert that electrical signal into sound, let's say, and then this is how you can hear me. Okay, so let's talk about the base of the speaker work, we can say. So application of the magnetic force on a current, let's say. All right, so one of the things that we have is basically loudspeakers use magnetic force to produce a sound. That is the base, we can say, of the loudspeaker here. Okay, so we can say, of course, the loudspeaker uses a magnetic force which is acting on a carrying wire in a magnetic field to produce a sound wave. So what are the parts of a speaker or a loudspeaker? All right, so take a look here. The parts that we have normally are all written here, or you can see them here. So we have a permanent magnet, you can see, okay? So that is one thing that we have. And of course, we have a coil of wire, you can say, and of course, we have a paper cone as well. In order to be more specific, we can say a coil of wire, as you can see there, and of course, a permanent magnet. That would be the magnet here, which obviously this coil is free to move, you can say, and of course, we'll talk about the importance of this as well. And then a flexible paper cone, which is attached to the coil, and then that acts as a speaker. Okay, so what happens exactly when there is a varying, or when there is an electrical signal that goes to the speaker there? Okay, so you can see here, this coil basically receives, imagine this coil, for example, like a solenoid there. We said when current moves, for example, or when current flows for, let's say, in one direction to another, let's say this is one of the directions that we have for something like this. Okay, so of course, when current goes, let's say, from one direction into another, let's say current flows in this direction here, and of course, we can say if that is the case, in order to be more specific, let's determine the direction, or let's say this is the direction of the current. So in this case, of course, this side is going to be north, and of course, the other side is going to be south here. And of course, now we have north and south created here. This north and south, of course, there is another north in there. So what happens when we have two north pole, let's say, two magnetic forces, and of course, these magnetic forces are, let's say, alike. Okay, and of course, or magnetic fields, let's say, and of course these two would repel one another. But since it is an electrical field, you can say this, or the polarity of this electrical field is moving. So at the first point here, you can say that this coil, of course the coil is movable, the coil will be pulled or pushed outside, let's say. So of course now you can say this cone here would produce a ripple outside, or you can say produces a compression here. And then of course, let's say for the other half of the signal, let's say, and of course the polarity of the electrical current will change here. So let's say this time, of course, it becomes, let's just say, becomes a south pole this time. And of course, the other side is going to be north pole. And we do know that south and north, of course, they will attract one another. So you can see here, this paper cone here, of course, will be repeatedly and continuously moving back and forth, back and forth, back and forth. This back and forth, of course, it is going to convert this varying electrical signal into a sound wave. And of course, the intensity of this depends on the intensity of the electrical current as well. Let's say how big, or let's say how small, let's say, these waves that are created, let's say, or the intensity of the sound generally, let's say. Okay, so this is how basically loudspeakers work. In order to understand this more, of course, we can say in a loudspeaker, when the direction of the magnitude of the current in the coil of the wire change, the paper cone attached to the coil moves, you can say, back and forth, producing a sound wave here. Okay, this is how normally sound waves are produced, let's say. Okay, so if we go through the details of this, we can say in a speaker system, a sound signal is converted to a varying electrical signal by a microphone. And by the way, we call these devices transducers, those that convert something to electrical signal or electrical signal to any other signal, or you can say any other types. Okay, then after that, after we've received, let's say, the sound signal and have converted to an electrical signal using a microphone, then the next step would be this electrical signal is amplified using the amplifier, of course, and then sent to the loudspeaker. And then after that, at the loudspeaker, this varying, remember, it has to be a varying or a change, let's say, an electrical current, but this electrical current has to be changing so that, of course, this paper cone keeps moving back and forth, you can say, okay? So electrical current causes a varying magnetic force on the coil. Of course, this magnetic force, of course, will increase, decrease. Based on that, you can say will convert, or based on that, you can say it will change the motion of this paper cone. Okay. And then you can say this alternating force of the coil results in a vibration of the attached cone, which produces a vibration in the density of the air in front of it. So, of course, this back and forth movement, there are air particles here. So when this paper cone moves back and forth, of course, it produces, let's say, regions where air particles are compressed, regions of, let's say, where air particles are dense, all right? Or you can say the pressure is high, and then, of course, when it goes backward, there will be other regions when there are less particles, less density, less pressure there. So simply you can say produces compressions and rarefactions. Okay. In this way, an electrical signal will be converted to a sound wave. Okay. Now, what does the operation of a speaker depend on? Remember this. This is one of the most important questions that we have here. It depends on the magnetic force exerted on a carrying wire within a magnetic field here. Okay, so what we have is this. There is a wire, which is basically the coil in here, that this coil is carrying an electrical current, and this electrical current, or the intensity of the electrical current, you can say, can change, and of course, which is inside a magnetic field, and of course, these changes would cause the back and forth movement of the loudspeaker, and this is how sounds are created, because basically sounds are created by, let's say, by vibration. So this makes the air vibrate, or the paper cone vibrate, and then this vibration will be transferred to the air, surrounding air, and this is how it can cause, or you can produce a sound wave. Okay, now let's talk about something else, which is galvanometer. Once again, you might say, what is the connection between a speaker, a loudspeaker, and a galvanometer? And of course, they are related because they are both, you can say, use the, we can say magnetic force, yeah? Or you can say a magnetic force on a carrying current wire, you can say. All right, so we have a galvanometer. What is a galvanometer, guys? A galvanometer is a device, basically, or you can say usually is used in the construction of both ammeters and voltmeters. Now, something very important you need to know is this. Galvanometers normally measure very low currents of order of milliamps or microampere. So basically, galvanometers are used to measure the currents in a range of milliampere to microampere, and of course this is a WSAT question, so you have to be very careful with, because if the amount of the current, let's say, is bigger than that, let's say, of course we have other devices like ammeters to measure the electrical current, and of course in order to measure the voltmeter or the voltage, we have voltmeter. But if the range of this current is very low, then of course we can use them to measure the currents in a range of milliamperes or microamperes. And of course now we're going to see that we can use galvanometers as ammeters or voltmeters if, let's say, if we have a small amount, let's say, of current or voltage. Of course, if it is small enough, we can use a galvanometer to measure them as well. Okay, but remember this, normally galvanometers are used to measure currents of ranges of milli or micro. So how does a galvanometer works? We're going to dive into the details in a second. But what does the operation of a galvanometer depends on, okay? So we can say it depends on the fact that a torque, okay? Now you might say, what about a force? Didn't we say a force? Well, this time we have a torque, and I'll tell you why a torque, not just a force. Okay. Let's say for the microphone, there was a force acting on the coil, let's say, or the paper cone acting on the coil, which was attached to the paper cone, and then of course this force would have made the paper cone move back and forth. But this time it's a little bit different. Instead of calling it a force, we call it a torque. And when do we use a torque? When there is rotation, yeah? And of course, let's say if this is the galvanometer needle, because it has a needle, it has a pointer. Let's say if it is basically, normally if it is vertical, that means it is reading straight. I mean, if it is vertical, basically it's reading 0. And of course, let's say if current is one direction, it can, let's say, shift into one direction. And of course, the bigger the intensity of the current, you can say, the more this needle is going to shift here. So when there is no current, of course, there's a spring that returns this one back to 0. And of course, if you change the polarity of the current, then it will shift into other direction. But normally it, let's say, stays vertical, just something like this one here. It can shift either right or left, you can say. That is basically your right or left. Okay, so now what does the, going back to this, what does the operation of a galvanometer depend on? We can say it depends on the fact that a torque acts on a current loop, okay? A torque acts on a current loop in the presence of a magnetic field. Okay, so now we are going to talk about the parts of the galvanometer. And of course, then I'll tell you why a torque, not just a force, okay? Now, let's talk about the parts of a galvanometer first. What does the galvanometer consist of, and how does it work? The first thing that we can say is we have a coil of wire. So you can take a look here, or you can take a look at this one here as well. So we have a coil of wire, and then we have a soft iron core, which is mounted so that it is free to pivot in the magnetic field. Or you can say something like this needle, you can say as well, okay? And then, of course, we have a permanent magnet as well. So how does it work, guys? Take a look at, in order to understand the working of a galvanometer, you can look at this one here. So we have a wire, basically, this wire is connected to the coil here. Or you can say, you can look at this one here. At this point here, you can see that the current is going into, for example, or goes like this way, yeah? So if that is the case, you can say there is a magnetic field around the wire due to the current that is passing through that wire or that coil. So of course we have a magnetic field here. And then this wire, of course, is going to come out in the other way. You can see a point which indicates that the direction of the current is outward, you can say, at this point here. So of course there is another magnetic field in that, you can say, around this wire as well. But since we have a coil, so of course we have two magnetic fields. One of them is by the permanent magnets, okay, and then the other one is by the wire, or you can say current carrying wire, or you can call it a coil if you want to be more precise in here. So these two, you can say, or the magnetic field of these two here, of course, are contradicting, you can say, or you can say opposing one another. Because of these two magnetic forces are opposing one another, so you can say that there is a magnetic force basically acting, you can say, downward on this one, and there is a magnetic force acting upward on this one. So these two both together are acting or making the needle, this pointer here, to shift, let's say, to the right. So instead of just a force, let's say, making this needle move, let's say, right or left, they are going to turn the needle. This is why we call it a torque, not a force, because torque is basically the turning effect, you can say, of a force. Yeah? That will be simply in that one. Okay, so once again, there will be a torque. This torque, where you can say this force, of course, will make the needle shift or move, or the pointer move, let's say. And of course, the bigger the intensity of the current that is passing through the coil, the wire, and of course, the bigger the opposition, or you can say, between these two magnetic fields. And of course, so this needle, of course, would shift, would let's say, move more, indicating that there is a more, or you can say, bigger current passing through that wire. And of course, you can see here there is, by the way, that is as much, or you can say, as long as there is a current that is passing through the wire here. But what happens when there is no current in the wire? And of course, there is a spring here. This spring, of course, it will return the needle, let's say, back to, this needle, of course, would return the needle back to 0 point, or you can say, calibrating this. And of course, then it is ready to be used or to measure another current. What happens when you switch the direction or reverse the direction of the current? And of course, now the force, of course, is going to be reversed. Okay, and then this time the needle is going to shift in the other direction, and then this is how it is going to read, or let's say, measure the current. Okay, so this is basically the core concept of the work of a galvanometer. And of course, there are different, let's say, pictures just to help you understand how it works more and more. And this is another picture, let's say, that is basically what you see from outside. And these are basically the parts that are from inside. Okay, so once again, let's go through the work again. Let's say a torque is experienced basically, or the torque experienced by the coil is proportional, directly proportional to the current in the coil. That is one. This means that the larger the current, the greater the torque, and the more the coil will rotate before the spring tightens enough to stop the movement. You can say the more the current, the more this needle shifts, let's say. Okay. And then, of course, the amount of deflection of the needle is proportional to the current in the coil. And then what happens if there's no current? If there's no current, this, you can say, needle will go back to 0, or you can say the spring will return the needle back to 0. This is normally what is a galvanometer and how it is working simply. Okay, now since we've learned what is a galvanometer and how it works and what is used for, of course, now we're going to talk about is this. Can we use a galvanometer as an ammeter or a voltmeter? Let's say as an ammeter so that we can measure the current, but of course it has to be in low value, let's say. And can we use it as a voltmeter so that we can measure the voltage or the potential difference or the electromotive force? For the answer is yes. Okay, but of course there are conditions in order to be able to use a galvanometer as an ammeter or as a voltmeter. Okay, so let's talk about the first part first, okay? How can a galvanometer be used as an ordinary ammeter? Okay, so remember this, guys. If we want to use a galvanometer as an ammeter, we must, remember this, we must connect, you can say, a resistor in parallel to that voltmeter. And of course, I'll tell you why is this. By connecting, we can say a resistor. Remember this, these are Wrya material questions, you can say, yeah? So these are very important. The question you will be asked is this: how can we convert or use a galvanometer as an ammeter? So your answer must be this: by connecting a resistor, a very low resistance in parallel with a galvanometer, because these are where the confusion comes from. So you have to be really careful whether the galvanometer or the value of the resistor is very high or very low. That is one. And then second, is it connected, or should it be connected parallel or in series? And of course, it has to be in parallel. And I'll tell you the reason why in parallel in a second. Okay, so let's talk about this. Why in parallel? All right. So of course, in grade 11, we've talked about. I mean, you've learned about series and parallel circuit. Okay, so let's say this is. Let's talk about parallel circuit first. Okay, so let's say this is basically a parallel circuit here. These are connected, and let's say this is positive, this is negative. Of course, these are electrical components. You can call them light bulbs as well. In parallel circuit, of course, we do know that, let's say the voltage here, let's use this one. Okay. How about if I just, okay, let's use this one. Remember this, in parallel circuit, V total is the same as, let's say, this, let's call it V1, V2, and V3, yeah? So we can say V total is the same as V1, which is the same as V2, which is the same as V3 as well. But one thing that is different in parallel circuit, of course, the current is additive. What do we mean by this? In another word, we can say I total is equal to I1 or additive, yeah, plus I2 plus I3. Okay, in another word here, for example, if I have 12 volt, there will be 12 volt on this light bulb, 12 volt on this light bulb, and 12 volt on this light bulb as well. But if I have, let's say I have, how about, let's say 6 amperes passing through the circuit in this case. If there is 6 amperes here, then of course, if these light bulbs are identical, then of course, 2 amperes are going, let's say, through this branch or this loop. 2 amperes is going to pass through this one here. So let's write 2 amperes differently here. Okay, so 2 amperes passing here, 2 amperes flowing here, and 2 amperes over there as well. So if we're going to add the total, of course, you are going to get 6 amperes in total. So basically, that is why we say the current is additive. And of course, a few more properties about parallel component here. You can see that the devices are connected individually, you can say, or the devices are connected in separate loop, or you can say in parallel circuit there is more than one loop. And another property is this: if one of these doesn't work, then the remaining circuit, of course, will work just fine here. Okay, which is unlike the series circuit. Let's talk about series circuit as well. Okay, and then let's say this is a series circuit here. Let's say this is 1, this is 2, and this is, we have 3 light bulbs, and this is, let's say, the voltage here. And then again, we have 12 volt. Okay, and the current that I have, let's say, is 1 ampere here. Let's say this is the ammeter that measures the current here. So if it is 1 ampere, if that is the current here, because it is series circuit, we have one loop, so you can say, if this is component 1, you can call this one I1, I2, and I3, which are basically, these are all the same. So in series circuit here, remember, the current is the same, which is opposite to parallel circuit. So of course we can say I total is the same as I1, which is the same as I2, which is the same as I3. So the same current will pass through each one of these components here. But what is different is the voltage. The voltage in series circuit is additive, or V total equals to V1 plus V2 plus V3. In another word, for example, if these are identical light bulbs, and if we have 12 volt, of course, there will be 4 volt on this one, 4 volt on this one, and of course 4 volt on the other one as well. So of course you get a total of 12 volt in here. And then, but another, you can say, another 2 differences is this. There is one loop, the devices are connected one after another. That is for series circuit. If one of them doesn't work, you can see. So let's just say that one of these devices doesn't work. Imagine if this one doesn't work, then of course the circuit will break. Or the circuit, let's say, there is a gap in the circuit, so the whole or the entire circuit is not going to work in this case. This is another major difference between parallel and series circuit. Now let's go back to the main thing that we were talking about, which is basically why do we need, let's say if we're going to get or use a galvanometer as an ammeter, let's say why do we need to connect a resistance, but remember this resistance connected in parallel with the circuit. So let's talk about this one in a detail. Okay, so let's say this is basically that what we have, right? Here is a circuit, and of course let's say this is the galvanometer that we're going to use as an ammeter. Okay, so remember this, we're going to connect a resistor with this, but remember these are in series circuit here, in parallel. Now watch this, guys. We said in parallel circuit, the voltage is the same. So whatever the voltage is here, you can call it V total, is the same as the voltage that is over the galvanometer, which is basically the same thing as the voltage over the resistance as well. So let me write VR, that is basically means the resistance on this one here. Okay, what about the current here? We can't say the same for current. Current, or I total, basically, right, would be, because we said in parallel the current is additive, would normally equal to the current that is on the galvanometer plus the current that is basically on this resistance as well, you can say, or let's just call it IR at this point right here. So because we said galvanometers has not the ability to measure, how about we say it this way? A galvanometer cannot measure, let's say, if the current is too much, yeah? So what we want is this. We want to use this galvanometer as an ammeter, but remember this. If that is the case, we should do something so that the minimum current value passes through the galvanometer so that we can still use it without damaging the galvanometer as an ammeter. And of course, at the same time, let's say we can connect it to the circuit as well. And we can do that by, let's say, doing something so that most of the current that we have, okay, will pass through the resistor instead of passing through the galvanometer. Because let's say if we have, let's say if we have 10 amperes, let's say. And of course, if 10 ampere passes through a galvanometer, there is a, let's say, potential, or there is a risk that might damage this, yeah? And of course, we do know that. So we're going to do something so that most of the current that we have will pass through this resistor, and only small part, we can say, will pass through the galvanometer. And how can we do this? I want you to think of this now. Imagine these grids, for example, as, let's say, water pipes here, okay? We have too much water, and there is a valve or there is a gate here. We don't want too much water to pass through this. What can you do so that most of the water will pass through this part of the component or this part of the pipe, if you want to compare it to that one? So of course, here we're going to do, yeah? We're going to make sure that this pipe is, let's say, wide enough so that most of the water will pass through this one, and then of course end up, let's say, at this point right here. Let's call it point B here. Okay, so how can we do that? Once again, by making this pipe large enough, wide enough, so that most of the water will flow through this one. And then of course, even if a small amount of water passes through this one, then of course this valve, or whatever you call it, is going to be safe enough. We're going to use the same technique with electricity. By the way, you do know that electrical current will always try to pass or flow through a wire or a component that has the least resistance. So what we're going to do is this. We're going to use a small resistor here, all right? And of course, then you can say the resistance of this galvanometer will be bigger than the resistor of, or you can say the resistance of this one is not that big compared to this one, so most of the current will pass through this loop, and then of course it can reach or pass through point B. And how can we do that? We can do that by using a small resistor here. So this R that we're going to use here must be very small, because if the resistance is big, then most of the current will pass through the galvanometer, then of course it could ruin or damage the galvanometer. We don't want that, we want the opposite. We want small amount of current to pass through the galvanometer, but most of them go through the resistor. Then, of course, we can use this galvanometer as an ammeter. Okay, so this is basically what we're going to do. So once again, going back to this, how we can convert a galvanometer to an ammeter, we can do that by connecting a resistance, a very low resistance, with a galvanometer, but it has to be in parallel with that, so that most of the current will pass through this one and then make it up to the other point. This is how we can do that, yeah? But what do we call this small resistance here? Of course, we're going to call it a shunt resistor. Why do we call it a shunt resistor? Or what is a shunt resistor? You can say it is a resistor that draws most of the current, okay, in the circuit, or you can say it is a resistor that has a small resistance which basically draws most of the current or allows most of the current to pass through this one, so that we can, of course, use the galvanometer safely here. So this is basically what you need to know, okay? So remember the answer, or how you can answer the question, how we can use a galvanometer as an ordinary ammeter. That is basically what it is, and basically this is what happens. So once again, what is a shunt resistor? We call this small resistor a shunt resistor. It is a resistor that draws, that you can say allows most of the main current, and of course leaves only very small current to pass through the galvanometer, which could be measured easily. And don't forget, current and resistance are inversely proportional. So the bigger the current, the bigger the resistor, the less current can pass. The smaller the resistor, the more the current can pass. So this is a short abbreviation for how we can convert a galvanometer to an ammeter. That is normally basically by a galvanometer with connecting a galvanometer with a small resistor, but this resistor has to be in parallel. Okay, and then once again, we went through this one here, by the way. So I total, because we are using a parallel circuit here, don't forget, okay? So we can say, let's go back to this. Okay, so this is, we can call this at I total, yeah? That is the current here. Once again, let's call this one 10 amperes, okay? Or let's say this value is 10 amperes. If that is the case, watch this. This resistor is very small, so we can say 9 amperes might pass through this resistor or this component, and then of course it can go all the way to the other end, and then maybe let's say only 1 ampere will pass through this side. If that is the case, then of course this current or the value of this current is very small. You can say not very small, but small enough so that we can use the galvanometer as an ordinary ammeter safely here. And then of course once it goes back, these two currents will combine. Of course we get a current of 10 ampere as a total as well. But remember this, there is 10 amperes because in parallel the current is additive, which means that the current split here. Whichever the part that has less resistance, more current will pass through that part. So this one has a small resistance, so most of the current will pass through this one, something like 9 ampere. That is for an example. And then 1 ampere goes through the other one, and that is how it can be used. So you can see here, but since it is a parallel circuit, the voltage is the same. So total voltage is the same as the voltage on the galvanometer, which is the same as the voltage on the resistor. One thing before I forget, if we want to find the current on the galvanometer, we can simply say, remember, this was the total, okay? And let's say this is the current on the resistor, and this is the current on the galvanometer. You can call it the ammeter now if we're going to use this one as well. So in this case, by the way, this is the total. This is going to split at this point here. So we can say I total equals to I on the galvanometer plus the current on the small resistor here. So of course, if we're going to find this one on the galvanometer equal to total minus the current that is passing through the resistor here or the small resistor. This is how we can do that. And by the way, if you're given enough information, guys, you do know that this one here, basically, the current on the galvanometer, you can use Ohm's law if you want to as well, yeah? So basically, voltage equal to current times the resistance, and then giving the voltage and the resistance, of course, you can find the current on each as well. That depends on what is given in the question. Soon we shall solve some. Okay. Now this time, how can a galvanometer be used as a voltmeter? That is the opposite to what we had before, yeah? First time, how we can convert or use a galvanometer as an ammeter. This time, how can we use a galvanometer as a voltmeter? Okay, now what is the nature of a, let's say, the voltage and the current in series? We did talk about this one, yeah? In series circuit, remember this, the current is the same. That means I total is the same as the current that is, let's say, on the galvanometer, which is the same as the current that is on the resistor here. But we're trying to use the galvanometer as a voltmeter. And how can we do that? Remember this, in series circuit, the voltage is additive, or the potential difference is additive. In another word, V total is equal to the voltage on the galvanometer plus the voltage on the resistor here. So once again, if we are willing to use this voltmeter as, watch this. I hope I wrote it nice enough. Let me just rewrite this one so that you can see what I mean by this. So V total equals to the voltage on the galvanometer plus the voltage on the resistor here. Once again, let's say we have 10 volts, let's just say, okay? So remember this galvanometer does not have the ability to measure, let's say, voltage if the value is too much, yeah? So how can we lower the voltage on this galvanometer as much as possible? Well, there is one thing we can do. If I have 10 voltage, let's say I'll make this one 9 volt, all right? And then I'll leave behind 1 volt for this one. If that is the case, 1 volt, I think it is quite enough, let's say, for a galvanometer, let's say, or good enough for a galvanometer to be able to measure this one. But how can I do this one? Right? Remember this, guys. If I want, or you can say, if that is the case, the voltage on this resistor must be very big. But we said voltage normally, using Ohm's law here, equals to what? Equals to current times resistor. We said the current is always the same, so there's nothing we can do with this one, yeah? But there is one thing we can do with the resistor. So by increasing the resistance, we can increase this voltage. If we increase this voltage, there will be less voltage left for the galvanometer because the total is fixed, which is 10. If I have 10, if I use a big resistor, then of course the voltage will be mostly on this component here. Only a small amount will be over the galvanometer. Then of course we can use it as a voltmeter. And that is of course the core or you can say the answer to this. So if we go back to the question, or to that question, how can we use a voltmeter, how can we use a galvanometer as a voltmeter or as an ordinary voltmeter? The answer is this, yeah? By connecting a resistor, but this time it has to be a very big resistor. Why? So that most of the voltage would be, let's say, over this resistor. All right, and this resistor, you can see that it is connected in parallel or in series. Of course, it is connected in series with the voltmeter, you can say. So going back to this, we can say we can convert, or we can use a voltmeter, galvanometer as an ordinary voltmeter by connecting a resistance of a very big resistance in series with the galvanometer. Then we can do that, of course. Now, then we can use the voltmeter. We can use the galvanometer as an ammeter. So once again, in series, the current is the same in, let's say, in series circuit, but the voltage is additive here. Okay, but normally, guys, if they ever ask you, for example, what device is normally used to measure the current, that is only an ammeter, okay? What device is used to measure the potential difference, the electromotive force, that is a voltmeter, okay? But what device is used to measure currents of, let's say, in a range of milliamperes or microamperes, then that is a galvanometer. I want you to make sure that you understood this one. Okay, now we have a question. Now let's talk about or see how we can answer questions related to galvanometers that are used as an ordinary ammeter or voltmeters. So the first thing that we have says we want to use an ammeter of internal resistance of 5 ohms in order to measure electrical current of intensities up to 10 amperes. By the way, whenever it gives you something like this, normally the value of the current, the biggest value of the current that is given in such questions, or most of the time, are the total currents, okay? But not necessarily like 100%, yeah? Because you really have to be careful about the contents of the question. Okay, but more likely, the highest or the biggest value of the current that is given is more likely going to be the total. Okay, so let's say we want to use an ammeter of internal resistance, okay? So we can say the internal resistance of the ammeter, or you can say galvanometer resistance if you want to call it, yeah? Okay, we're going to switch it up just in a second, but remember this, that is basically 5 ohms. That is first, yeah? Says in order to measure an electrical current of intensity is 10 ampere. So of course, now that is going to be, if that is the case, then this is going to be the total, which is 10 amperes, while the ammeter measures currents between 0 to 1 ampere. That means, for example, if this is the current on the ammeter, you can say from 0 to 1. So maximum current that we're going to measure is basically 1 amperes. Okay, 1 amperes. Let's make this one nicer. 1 amperes. Okay, next says, what is the resistance of the shunt that should be connected in parallel with an ammeter in order to do this job here? So we can do, of course, something like this. Let's say if that is the case, we can call this one the ammeter. That is basically galvanometer, that we will use this as an ammeter. This is the resistance that we're going to connect with. And remember, this resistance has to be connected in parallel. We said the value of this resistor must be small, yes? So that it can draw most of the current through this loop, or you can say through this component here, and then of course we can make it there. So we can say this is basically I total, all right? And of course, if we have V total, we can say, because it is parallel, V total will be the same as, let's say, the voltage over the ammeter, you can say, which is the same as the voltage over the resistor as well. But in terms of current, I total here, there's different with the current that is on the ammeter, let's say, and of course, with the current that is basically on the resistor as well. Okay, so watch what we have here. We have, let's say, the resistance of the ammeter. Let's change this one to ammeter now. I think it is time. Okay, so the resistance of the ammeter, let me write it opposite. So this is the resistance of the ammeter, which is 5 ohms, you can say. This is not 0.5, just 5. Okay, and then we have the I total, which is basically 10, and of course we have I for the on the ammeter, which is basically 1 ampere. So what is the resistance of this one right here? Or how can we find this resistor? First of all, we're going to find a few things first, yeah? So one of the things that we have is this. We have I total, okay? And of course, what is I total equal to? We can write the equation, yeah? I total here, we said it earlier, let's write a different color. Perhaps it would be best. All right. So we can say I total here equals to I on the ammeter plus the current on the resistor here. That is one thing simply we can use, yeah? So I total is basically, we said it is 10 ampere. The I on the ammeter is basically 1, yeah? So plus I on the resistor, because we don't know what is the value for this one. So I on the resistor, okay? If you take this one to the other side, of course, or this one to the other side, it becomes 10 minus 1, that is going to be 9 amperes. So now we know one thing, that the current that is basically here is going to be 9 amperes here. Now, if you know this one, of course, the remaining part is going to be easy enough. That is the first part, yeah? So now we know the current, yes? I mean, we do know the current. We do know the current for each one of these, yeah? So next is by finding the resistance of this one, and how we can do that. By using Ohm's law, you can say, yeah? We do know that V total, we said it is the same as the voltage that is on the ammeter, which is the same as the voltage on the resistor. So can I say the voltage here is the same as the voltage here? Yes, if I can do that, of course, then I can find the answer to this one here. Or I can, perhaps I can do something else, yeah? I can say, obviously, VI total, which I believe I don't need that one, yeah? So in this case, we can say V on the ammeter, or voltage on the ammeter, is the same as the voltage on the resistor as well. But we do know that V on the ammeter, using Ohm's law, you can say equal to I times the resistance of the ammeter, which is basically equals to I, that is for the resistance, yeah, times the R, the resistance of the resistor. All right, next, of course, if we're going to do this one here, the current that the ammeter reads is basically 1 amperes times the resistance of the ammeter, which is given, is basically 5 ohms, yeah? So that is 1, yeah? And of course, on the other side, the current that is passing through this resistor, we found, which was 9 amperes, multiplied by, let's forget the unit for now, 9 amperes multiplied by the resistor as well. So how can you find this one here? So of course, the resistor equals to 5 over 9, and of course, that is about 0.55, I believe. It was going to be ohms. Okay, oops, sorry, not this one. 5.5 ohms here. Now, if you take a look at this one here, the resistor of this resistance is basically about 0.55 ohms, yeah? But the resistor of the ammeter was 5 ohms here. So, of course, remember the analogy that I gave you? In order to allow most of the current to pass through this one, we said we're going to use a wide pipe, let's say. You can see here we have 5 ohm resistance here. We have 0.55 ohm resistor. So, of course, the resistance through this loop is way less than this one here. So, that is why most of the current will be drawn or will be allowed to pass through this loop and, of course, make it to the other side. And this is what we call it a shunt resistor resistance. So, of course, the resistance of the shunt resistor is about 0.55. We can double check with this number. I think it is 0.55. I hope I'm not wrong. Okay, so yes, it is. So that is basically the resistance of the shunt resistor. And of course, there are a lot of exotic questions. I would really want you to go through some of these. These are very, very important. Take a look at the first question. It says, which of the following can measure high electrical current? Remember, we cannot use galvanometer for that because the current is high. What about, so in this case, it's going to be ammeter, by the way, yeah? Because current, yeah? Which of the following can be used to measure high electrical potential or electric potential difference? If it is high potential difference, that means high voltage, that is, of course, voltmeter, not galvanometer. Okay. This one also, the very low resistance, which is connected in parallel with the galvanometer when it is converted to, let's say, or we want to convert to an ammeter, let's say, to be able to measure high current. That is called basically, what is it called? It is called a shunt resistor. Okay, and of course you can do the following there. Now we have another question here. Okay, what does it say? It says, a moving coil voltmeter measures potential difference between 0 to 5 volt here. If the resistance of a voltmeter is 500 ohm, calculate the intensity of the current through it if it reads, let's say, 5 volt. And then after that, we want to use this voltmeter to measure potential difference greater than 5 volt. What is the resistance of the resistor that should be connected in series with the voltmeter in order to measure a total potential difference of 30 volt and at one time, and of course another time with 100 50 volts. Okay, that is another question. We're going to use this one as well, or solve this one too. So stay with me. We're going to solve this one as well. This is also a very important question here. Move this up a little. Okay, take a look here. Basically says what? A moving coil voltmeter, okay, that is one, used, or let's say measures potential difference between 0 to 5. Okay, so we can say the voltage for this, we can, let's say this is a voltmeter. Let's say a voltmeter here. And of course, we're going to, for second part, we're going to connect a resistor with this one here. Okay, now, what do we have? This is 0 to 5 volt. And then the resistance of, if the resistance of the voltmeter is 500 ohms, that is the resistance of the voltmeter, calculate the intensity of the current that is passing basically through it when it reads 5 volt. So for the first part here, for this part, let's encircle this one perhaps. Let's say for this part specifically first, yeah. Using Ohm's law, we can say V equals to IR, yeah. Or you can say R equal to V over current, doesn't matter, just a matter of rearranging the equation. Says what is what? What is, or if the resistance this much, calculate the intensity of the current. So find the current. Current equals to basically V over R. Yeah. What is the voltage that this voltmeter is reading? That is basically 5 volt. Okay. And then divided by a resistor of, let's say, 500. Yeah. So of course, let's say 5 divided by 500. How much is this? That is 0.001. I hope, and that is going to be current. Yeah. Okay, because we're ampere, because we're trying to measure the current flow. Okay, now the second part for this says what? We want to use this voltmeter to measure potential difference, but greater than 5 volt, okay? What is the resistance of the resistor that we need, let's say, where is it? That should be connected in series with a voltmeter in order to measure the total potential difference of 1 volt here, 30 volt. So we have a total voltage now, we can say, which is basically 30 volt. By the way, we're just going to do this part first, okay? If that is the case, remember this. We have basically the current that passes through this one, and of course we have, let's say, we also have the resistance as well. What is the question here? What is the resistance? Let's say, basically, this resistance is unknown here. By the way, we do know that the current that passing through this one, of course, it must be the same as this because it is series. So the current passing through each one of these is going to be the same in here. Okay, now we can, there are a lot of things, by the way, we can do this in order to do this. Yeah, we have V total, we have the voltage on this. We can easily find the resistance of this one. That is one way. Another way is this, okay? What was the voltage of this? If this is basically 30 volt, okay? And then, of course, let me just make, by the way, this is 0 to 5. It is not 0.5 volt, yeah? If 5 volt is here and this is 30, how much voltage would be left for this one? Okay, so take a look, because the voltage is additive, like doing it just in a quick way. Let's say V total equals to basically the voltage over this voltmeter, let's say, and then plus, of course, the voltage over the resistor. If this is 30, the voltage was on the voltmeter was this, and of course the voltage on this one is basically, let's say, unknown. So VR is basically going to be 25 volt, if that is the case. And we do know that the current, because we found it before, so the current that is passing through here, it is all the, let's say, the same all the way, yeah? Because the current is the same. So the current is was 0.01, yeah? So multiplying this, or you can say V basically equals to IR, yes? So knowing the voltage, knowing the current, we can find the resistance over there. So what would be the resistance over there? We can say, by the way, this you can call it the fast way here. So we can say resistance equal to 25 volt divided by the current, which is 0.01. In this case, is, of course, is going to be 2,500 ohms, right? That is basically the resistance of the resistor. Remember we said the resistance has to be very big. So 2,500, of course, it is a big value. What is the other way? Or you can say the other way that we're going to do that, yeah? Of course, we can say the voltage here, okay? Or V total, we can say, there's another way, yeah? We can say V total, or comes from, you can say IR for total, yeah? But we can, like for example, let's just go ahead and do this one there. So of course we say V total equals to once again V on the voltmeter plus the voltage over the resistance here. But of course V total equal to IR total equals to let's say the current times the resistance of these are for the voltmeter by the way, plus the current multiplied by the resistance here. Okay, so the V total here, I think I don't have enough space left, so I'm going to erase the upper one here. So V total basically is going to be 30, yeah? And then of course the other one, remember, it was the current was 0.01 times, was 5 ohms, yeah? Yes, was it? No, actually it was 500, yeah? Okay, and then plus, watch this, IR, this is 0.01 times the resistance. So of course now, this is going to be 5, it goes to the other side, it goes to be 25 equal to 0.01 R, yes? And of course R equals to about 2,500 ohms as well. This is another way where we can do that, but I would recommend you whichever, I mean, perhaps the faster way might be easier as well. That is how you can do this question. I'm afraid that is all the time that we have for today. By the way, using 450 volt, it is literally the same thing, right? Just different numbers, okay? But I would recommend you try this one as well. Till then, inshallah, in the next lesson, we're going to start from section review 5.3, and hopefully it's going to be the last lesson in this section. Till then, keep practicing, and I'll see you soon. Assalamu alaikum wa rahmatullah.